the dynamo. And we heard in the earlier talks today that helicity has, it's very important concept for even the dynamo process. And because of very important reasons, we do see that helicity becomes a very important issue in the study of this dynamo and turbulent dynamo, mean field dynamo theory. Because astrophysically we know that in high So we heard in the previous talk, like in earlier talk by Kanuswamy Subramanian, that you see that helicity, if you go by the helicity evolution, it is something like this, where C is greater than 6. So we see that helicity puts a lot of constraint on the dynamics of the flow, and yeah. So we have some topological investigation in that how we can actually, it's just in terms of like links and knots, that how actually helicity, the information of the helicity is embedded in terms of the links and knots, and how the topology manifests itself in a variety of forms. But we have a little unique way of describing it in terms of the orientable and non-orientable surfaces, which will come as a demonstration at the end in terms of the Mobius spectrum, which we'll consider as a flux tube, and then we'll cut and do some allowed operations to show that how you can actually generate links, but actually not at the expense of the violation of this dH by dt. So you see that you start with no links, no knots, but you end up producing these numbers. But so how these informations are actually manifested very nicely. But we have some photographs here. You can see that there are many earlier works by like Moffat and many theoretical investigations which show that differential rotation and the turbulent convection may give rise to flux rings. And we know that helical dynamos are like very key issues for the growth of magnetic field, for the growth of mean magnetic field. So helicities are very important concepts. Yeah. We don't consider the reconnection and meaning in the high RM limit, we don't consider this, let's say the eta is equal to 0 case we are considering. So you can see some solar pictures, like pictures of the sun, in which the
laser pointed here,
in which you can see the plasma blobs and various structures. In terms of the helicity, actually has a kind of a screwness inside, like where A is equal to P is equal to curl of A. And in terms of the fluid helicity, if you write, so the equation can be written as V dot omega. Of course, its all quantities are averaged over volume. So omega is equal to vorticity. So these are some three-dimensional structures which are actually in the fluid. These informations are with the fluid, and they have very important constraints on the dynamics.
Nishan, well, there's a pause, but any visual picture like this, can you tell nothing about the vector potential, right? Vector potential isn't an observable quantity.
No.
So any twist that you can see can only refer to either kinetic helicity or to current helicity, right? But never to magnetic helicity. Magnetic helicity is unobservable.
Yeah, they're not
like any other potential, A is unobservable. Only in quantum physics it can be observed. This, in fact, was always puzzling me, how an unobservable quantity can be important for a physical process.
So I think Simon has some further say on. That actually this leads to something called realizability condition, which I think you will speak on.
Yeah. Okay, I hope you can all hear me clearly, also in the back. Okay. Now I will talk a bit about helicity and what helicity actually is. Well, today, of course, you've seen already this formula. Helicity is basically the volume integral of A dot B. And one very big importance of this quantity is the so-called realizability condition, which means that the magnetic energy on each scale is limited from below by the magnetic helicity, as you can see here. So as you see, there is a K here, which means that when you look at every scale of the magnetic energy, then this is bound from below. It's not the total energy, but it is scale. So, okay, now since we want to make the link to the linking number, I will show you how the helicity is connected to it. As a very simple example, take two flux tubes like this, C1 and C2. Each of them have a magnetic field in it. And then the flux of the vector potential through each of those loops here is just given by this line integral. And this, of course, can be written via Stokes' law like this. And the curl of A is, of course, B. And since you are only integrating over this surface here, the only contribution comes actually from B2, because B1 is 0 within the surface. So basically you get phi 2, which is the magnetic flux in this tube here. So now if you take two flux tubes which are not knotted, then you can calculate the helicity, the linking number via the helicity. And this is simply given by this is the helicity. And it's 2 times the magnetic flux of each of those tubes times the linking number. So if you have the magnetic helicity of the system, you just divide by the 2 fluxes of the 2 tubes, and by 2, and then you get the linking number of those 2. Then you know how often they are actually linked. Yeah, and the important point here is actually that knowing the change of the helicity gives you also some idea about the change of the topological structure of the system. So for example, should you have the case that the magnetic helicity changes rapidly, it might be the case that you break some links of those tubes. For example, you've got those two linked tubes and you break them completely, then the helicity should drop also.
Or be transferred to other forms, not necessarily drop. They can be rise, twist, right?
Yes, okay, but in this simple example I didn't consider like twisted tubes in this example. You're right, actually later in our example we will see that those internal twists of the tubes actually are in the helical sense equivalent to linking number. This we will actually see in this workshop. Okay, now we made some simulations with Fabio Del Sogno and Axel Brandenburg, and we are considering this system here. You have 3 flux tubes with a magnetic field which is going into the direction of the arrows here. And now the linking number of this one is 0 because of the direction of the magnetic field lines, and here magnetic fields lines are opposite. So the linking number is 2 in that case. We've got these two different cases. Linking number 0 and linking number 2. Which corresponds also to zero helicity and finite helicity. So then we ran the simulation and we were observing the magnetic energy and how it evolves in time. And this is shown here in this plot. This is the time and this is the magnetic energy. So in the solid line is the case with finite helicity, so this one. And the dashed line is the case with zero helicity. So what you can see is after a certain time, the magnetic energy behaves much faster in the zero helicity case than in the finite helicity case.
Sorry, what was exactly the model? So what drives the evolution? You have the initial state shown here, right? And what's then? Do you impose some velocities or what?
No, we've got zero velocities.
It's a free decay.
So then because of magnetic tension, they start shrinking.
Yes. Which you can also see in these two plots here. You see here plotted all the magnetic field lines, and at the same time, but this is the zero helicity case, this is the finite helicity case. And as you can see, zero helicity case, the structure, the initial structure is not anymore observable. So it's pretty much destroyed. While in the finite helicity case, the topological structure is still there. So you still can see those rings. Well, it's a bit difficult to see, but if a closer look, you can see the inner ring and the outer rings. So another thing which is happening here is actually that the upper rings, they're actually splitting up into two thinner rings in this simulation. But basically, topologically, it stays the same because they have only half the flux.
So, are those initial topologies inspired in a physical observation, or they are purely theoretical, just to see what we get?
Well, actually, there are just very simple model simulations. We just wanted to see how the topology can influence the dynamical evolution of the system. Actually, we don't really know any system where we have actually that magnetic structure. So,
Sorry, still, could you please explain it again? To me, these two diagrams look very similar to each other. What exactly is different between them? And what is shown with color? Is it b squared?
no, actually, it's the magnitude of B.
Oh, you mean then the result?
Yeah, but
No, he means the initial condition,
to me,
right?
they look very, very similar.
The initial condition or what?
No, he means the color coding.
Oh, that one.
So why you say that they are different? What's the difference between them?
One difference is because it's here you actually don't see any inner ring.
Neither in the bottom.
Well, actually,
You're
much
saying the
more
energy
than that.
decay law are different, right?
Sorry?
You're saying the decay laws of energy are different.
Yeah, exactly.
So it's a matter of principle question whether if you have a topologically complicated field but with zero helicity, does it still decay slow? That's the question that I thought you were trying to address.
And then this graph answers this question.
Yes.
Yeah.
It's enough.
Yes.
But then these colorful diagrams, I don't see what you can learn from them.
That is to
Well,
To me,
actually,
they both look very, very similar. I don't see any fundamental difference between them.
if you like, later I can show you the real three-dimensional model. I mean, of those diagrams. Then you can see it's much more clear.
It would be interesting also to completely decouple the three rings and ask whether that decay is even faster.
You mean you completely change the
I mean-
topology?
No. See, you have zero helicity but with some non-trivial topological quantity in that n equal to 0 case.
Yes.
But suppose you just have three separate rings, then they will also decay. And does it decay faster than the dash line?
Well, that I cannot say. We haven't checked that one. But you're absolutely right. I mean, you can have different topological structures with all helicity 0. And I think that's what you want to say, that actually you have some kind of topology here, right? I mean, which is different from 3 separate rings. So now the question which we don't know the answer for is, how do higher order topological quantities play a role in this? Actually, helicity is a quite low order number. So that's a good question, yeah.
So what is the definition of your grid, and there is any numerical resistivity that analyze the...
It's explicit. Resistivity.
I think the resistivity was kept very low actually. See that?
It's fixed.
Yeah, it's fixed, but it's quite low, so you don't have those reconnection effects.
Did you monitor helicity throughout the simulation? Did it stay relatively constant in the bottom model?
I don't think that. Do you have?
I thought you had a plot of that in your paper.
No, we don't have a.
What was the question?
I mean, if we have monitored the helicity.
Yeah. It decays slowly, very slowly.
So do you see a twisting of the field lines in the bottom plot once?
Basically, in both there will be local twisting, right? In both cases, there should be local
Twisting, there should be a net twisting at the bottom. Just wondering if there's some twisting of the field lines in the where there's helicity once these tubes move through each other.
I mean, in principle, you can calculate the total helicity by just either doing A dot B or by doing B, the full definition of the helicity as linkages between field lines. So, I thought, didn't you have it, Axel, or in your paper, didn't you have a plot of helicity at this time?
Well, it's not here, but yeah, it should be there. Okay. So.
It's very difficult to make this.
Okay, now this is a bit different than what I told before. This is a very handy way to calculate the linking number of two independent rings. So it's called. So basically, you just draw this diagrams here, and then you calculate the crossings, the number of crossings. And basically you have got this rule, so if you have got like the blue line or the red one with this velocity configuration, then it's a plus, the same for this one. And then you just go through this diagram and add up all the pluses and minuses. And the linking number then is simply the sum of all positive crossings minus the sum of all negative crossings divided by 2. So this helped us in other configurations a lot to compute actually the linking number, because when you see this node, this three-dimensional structure, I mean those two links, then it's quite difficult to determine actually the linking number. And actually later in our example, which we will show, is basically this one. So the example you will be doing later is actually this one, and then you can see that the linking number is actually 0.
This is how we computed the Ayuka linking number, 0.
But, sorry, but in 3 dimensions, this calculation can give different results depending on your viewing angle, right? So what you do, average or what?
No, the linking numbers are topological invariant.
Doesn't depend on
Yeah,
projection,
you just
right?
project.
No, I believe it does not depend at all, because if you look in a different angle, you might get different crossings, but the sum should be the same. I mean, this statement is true for single nodes, when you consider only single nodes, not two independent things. Okay, maybe you should do the earlier section. This is from
We'll first distribute some pages. We'll do some experiment here. You can do there together.
I've got one question actually. Can we just go back one slide before we lose you? The picture with the big picture where that goes flux. That one, yeah. You've drawn attention to the different topological connections of those pictures, yeah? But if you look on the left-hand picture there, in the middle of that grid, yeah, you've got flux going one way, in very close proximity to flux going the other way. Yeah?
Yeah, well, basically, there are
That's right, yeah. And in the other picture, you've got flux in close proximity to flux going the same way.
Yes.
So that in the left-hand one, just locally, there's going to be far more confusion just across that central region in the middle of those rings, yeah, than there is in the right-hand one.
Yes, I don't think it's together.
So you'd expect that left-hand one to produce faster decay of magnetic energy than the right-hand one. Even if you reconnected the things in a completely new way, I mean, if you took the left-hand one, you put it up together,
You need scissors and
reconnected
don't
it a
have
long way away.
but you keep
You
the
still wouldn't change what's happening in that central region, on that very high dissipation region there. So, and what I'm trying to get at is that, is it really the topological connection which is crucial here, or is it actually the fact that there's far more low dissipation on the left than there is on the right?
Yeah, well, of course you're right. It's, this is strongly influencing the dynamics. But I would say it's not a crucial part. I mean, the crucial part is really the topology. First of all, because of the realizability condition. I mean, you can always make very thin rings and put them very far apart. I mean, those outer ones, they are not really influencing each other. And then you should get qualitatively the same result.
Of course, Chris is right. It is always the dissipation which leads to dissipation. Obviously. But the question is, how come you have more in one case than in the other?
But probably what Chris says is a direct consequence of different topology. Indeed, the geometry is different, but it's a consequence of different topology.
Well, no, it isn't just a consequence of different topology. I mean, what I'm saying is it's a consequence of the local behaviour, right, in that middle of the ring. And I think if you cut the rings up at the top and reconnect them in a different way, I don't think there's much difference to the graph.
Or if you got rid of the middle ring.
Or if you got rid of the middle ring altogether. Yeah.
Well, but then what Carlo suggested, just have a configuration with zero helicity, but in disconnected rings. But on the other hand, n equal to 0 to the left. But as Simon said, the higher order topological invariant with no 0 there. So it is a non-trivial topology, even though helicity is 0.
So if you take out this middle ring in here, what do you expect?
But wait a minute, I think Andrew Beckley can check this, because in Andrew Beckley's code, there is no magnetic diffusion observed. There, magnetic lines are reconnected directly. So, and Andrew can easily, I think you have everything ready just to repeat this calculation, right? But with your reconnection only.
You could just try 2 weak tubes Well, one unlinked and one linked.
Oh no, just exactly that. You can reproduce this, but now with the connection. So you have everything. Can you do it before the next week?
Yeah,
But why not? You were doing it on a day-to-day basis. Can you do it for the next week?
If you remove the middle ring, you lose the magneticity, so the decay should be fast. So it's really the presence of the middle ring which is very slowly.